Today we will be looking at 4.3, which is dealing with logarithmic functions. So, a logarithm can be defined as for all real numbers y and all positive numbers a and x, where a is not equal to 1, we have y equal to log base of a x, and that is going to be equivalent to x is equal to a raised to the y. So, our y here is going to be our exponent in our second portion right here. So there it is. And additionally, what do we have? We have this base of a, and we have our base a right there. So the expression log base of ax represents the exponent to which the base a must be raised to obtain our value of x. So we will be using these forms when we look at some of these examples here. So logarithmic form and then exponential form. Let's go ahead and try to convert between the two. So let's go ahead and try to convert from logarithmic form into exponential form for this first example. So what we have here is we have a base of 3, and then again our exponent here is going to be 4. So to make sense of this, what do we have? We have 3 raised to the 4, and that's going to be equal to 81, which logically makes sense. So additionally, let's try to go from exponential form back to logarithmic form. So here, what do we have? Well, we have the 1/2, and that is going to be our base, and then what's our exponent? Our exponent in this case is going to be that -3, and that's going to have just an 8. So let's go ahead and rewrite this. We will have a log. We said our base was 1/2, and then in this case our exponent was a -3, so that is what we will set it equal to. And then we have the 8. So log base of 1/2, 8 is equal to -3. Again, let's try to go from that logarithmic form into that exponential form. So our base is 10, so we have 10 raised to, in this case our exponent is this 3. So 10 raised to the 3 is equal to, what we have left over is that 1000, which again makes sense. So let's try to convert from exponential form back to logarithmic form. So our base again, what is it going to be? It's going to be that 5. So in this case we will have a log base of 5. And then that will be equal to our exponent, which in this case is -3. And then we have the 1 divided by 125. So, okay, so that should be our logarithmic form. Let's go ahead and look at these last two examples here. So we have a base of 12, so base 12. Our exponent, again, in this logarithmic form, it's going to be whatever it's equal to, so in this case a 1. And that's going to be equal to this 12 right here. So 12 to the 1 is equal to 12. All right, for our last example, let's go ahead and try to convert. So our base is going to be a 6, so log base 6 is equal to, what's our exponent? Our exponent is 0. And finally, what we have left is a 1. So log base of 6, 1 is equal to 0. Okay, so let's go ahead and try to solve some logarithmic equations here. So for our first logarithmic equation, we have log base of x, 16 divided by 9, and that is going to be equal to -2. So let's go ahead and try to convert this into some sort of form that might be useful. Let's look at this. What is our base here? Our base is going to be this x. And now our exponent, again, is going to be this -2. So what can we write? We can write our base of x and then raise it to, what's our exponent? -2. And that's going to be equal to 16 divided by 9. Now, we can go ahead and rewrite that x to the -2 by saying 1 divided by x squared, and that's going to be equal to 16/9. Now, the last step we want to do, multiply the x squared. So that will give us, in this case, a 1 is equal to 16/9 x squared. And then what do we want to do now? Well, we want to go ahead and try to isolate the x. So let's go ahead, divide by 16/9, divide by 16/9. So now that will get us 9/16 is equal to an x squared. Now, what we want to do is go ahead and try to further isolate the x. So let's take the square root of both sides. So in this case, what we need to do is go ahead and plus or minus. And the square root of 9 is going to give me a 3. Divided by square root of 16 is going to give me a 4. And that is going to be equal to x. So when dealing with logs, we actually don't want to have a negative value here. So in this case, our x is going to go ahead and be positive 3/4. Okay, so let's go ahead and look at our part B here. So for part B, we're dealing with log base of 16x, and that's going to be equal to 3/4. So again, we want to go ahead and rewrite this into some sort of form that is a little bit more useful. So our base that we're dealing with, again, is going to be a 16, and our exponent that we're dealing with is going to be this when we want to convert into exponential form. So 16, again, that's our base, is raised to our exponent, a 3/4, and that's going to be equal to x. And again, this form that I am using is coming from this portion right here. They are both equivalent to each other. So as we continue to look at this example, let's go ahead and try to rewrite the 16 to the 3/4 as the bottom number will be associated with our radical here. So the 4th root of 16, and then the top number, or the 3, is going to be what we raise it to. So that will give us the 4th root of 16 raised to the 3rd. So the 4th root of 16 is going to give me a 2 raised to the 3rd, and that's going to be equal to x. So in other words, we can say x is going to be equal to an 8. Okay, so let's go ahead and look at our C here. So C, in this case, log base 36, and then we have the square root of 6 equal to 6. So let's go ahead again and try to rewrite this one. Our base that we're dealing with is 36. Our exponent that we're dealing with is x, and that's going to be equal to the square root of 6. So 36 raised to the x is equal to the square root of 6. So let's go ahead and try to rewrite that square root of 6. So 36x is equal to 6 raised to the 1/2. Now, we can get this into something that would look a little bit familiar from previous chapters. Let's go ahead and try to get this 36 to have a common base as that 6 so that we can set our exponents equal to each other. So what times what will give us 36? Well, 6 times 6 gives us 36. In other words, 6 raised to the 2. So we can go ahead and say 6 squared x is equal to 6 raised to the 1/2. So now that we have a 6 and we have a 6, based off of our previous properties in our other chapters, we know that we can go ahead and set our exponents equal to each other. So that gives me a 2x is equal to a 1/2. Now let's divide by 2, and we are left with x is equal to positive 1/4. Okay, let's go ahead and look at logarithmic function here. So if a is greater than 0 and a is not equal to 1 and x is greater than 0, then the logarithmic function with base a is f of x is equal to log base a of x. So exponential and logarithmic functions are basically going to be our inverses of one another. So now we can go ahead and perform the steps in order to show that these two are inverses of one another. So first we start with f of x is equal to 2 raised to the x. We're just going to use this as an example. So first thing we know, we can go ahead and convert that. Y is equal to 2 raised to the x. And what do we do if we want to go ahead and find the inverse? Well, we can go ahead and interchange x and y. So interchange x and y. So we're going to go ahead and interchange our x and y. So x is now equal to 2 raised to the y. And we can go ahead and try to see what comes of this. So interchange x and y. What do we need to do next? Well, we can go ahead and convert this into another form that we know. So what do we have? Well, we have our base of 2. We have our exponent, in this case of y, and that is equal to x. So based off of what we previously know, we know that this is equivalent to, in this case, a log. What was our base? Our base was 2. And then we'll have x is equal to, what is our exponent? Well, our exponent was y. So our last step that we need to do is go ahead and replace y with f inverse of x. So let's go ahead and replace y with f inverse x, which should give us, in this case, a log base 2 and then an x. So we should be good to go there. Okay, so additionally, what do we have? Well, we have some characteristics of the graph of f of x is equal to log base a of x. So one thing that we can quickly note is that the points 1 divided by a, comma -1, 1, 0, a1, they are going to be on the graphs. Additionally, if a is greater than 1, then f is an increasing function. Now, if a is between 0 and 1, then we're going to have a decreasing function. The y-axis is going to act as a vertical asymptote, as well as the domain. It's going to be 0 to infinity, and last, our range is going to be from -infinity to +infinity. So with these kind of characteristics in mind, we can go ahead and look at some of these logarithmic functions and what their graphs are going to look like. So for this first one, we're going to go ahead and use our first method, which says to use the inverse and reflect over y is equal to x. Then we're going to go ahead and interchange our ordered pairs, which should give us our desired graph. So the graph that we want to go ahead and look at is log base of 1/3 x. We need to figure out if we can rewrite this in some sort of way. So we know that we are dealing with, in this case, f of x is equal to, and we said log base of 1/3 x. So we know that that is equal to y equal log base of 1/3 x. So we're dealing with, in this case, a base of 1/3, and in this case, our exponent would be a y. So let's go ahead and highlight that. So we can write this in exponential form. So we know that our base is 1/3. So we can take 1/3 and raise it to, again, our y is highlighted in pink here, and that is equal to x. Now, we can go ahead and interchange our x and our y to get us our desired graph. So let's go ahead for this first portion here and fill it in now. So let's go ahead and interchange our x and our y. So interchange x and y, and go ahead and plug it up here. So now our y is going to be equal to 1/3 raised to the x. Now 1/3 raised to the x, we need to go ahead and figure out some points for this. So let's go ahead and figure out some points. First, let's pick a 0. So if we plug in a 0, we will get a y value of, in this case, a 1/3 to a 0, or just a 1. A -1 should give us a +3 here, and then a -2 should get us a +9, and then a 1 should give us a 1/3, and then last we would get a 2 and then a 1/9. So next we need to go ahead and interchange our ordered pairs here. So interchanging our ordered pairs, all we're going to do is switch x and y. So this now becomes 9, -2, 3, -1, 1, 0, and 1/3, 1, and then finally 1/9 and 2. So we can go ahead and figure out what this graph is going to look like. So now we have a point of 1, 0. We have a point of 1/3, 1, So that will approximately be right here. And we have 1/9 at 2. And additionally, we have points at +3 and then -1 and all the way at +9, -2. So this graph should approximately look like this. Okay, so we are good to go for that example. We can go ahead and look at our second one here. So we're dealing with log base of 2 and then x minus 3 and then finally plus a 2. So let's go ahead and figure out what is going to happen in this specific example. So based on what we previously know, we can go ahead and guess that this x minus 3 tells us that we're going to go ahead and move to the right 3. And this +2 tells us that we're probably going to go up 2 in this case. So what do we want to do? We want to use our second method available to us, which is use our exponential form and then pick our y's first. So our exponential form, let's go ahead and figure out what that'll be. That will give us a y equal to log base of 2, x minus 3 plus 2. So our base is going to go ahead and be, in this case, the 2, but we need to go ahead and take care of that +2 tacked on to the end. So go ahead and subtract a 2. That leaves you with y minus 2 is equal to log base 2, x minus 3. And now what you can do is go ahead and take the 2, which is going to be your base, and raise it to your exponent, which is going to be that y minus 2. So the 2 is going to be our base, and the y minus 2 is going to be our exponent. So in this case, we will be left with a 2 raised to the y minus 2, and that's going to be equal to, what do we have left over? Well, an x minus 3. So we can go ahead and do some final configurations to this. Go ahead and add the 3 over. And that leaves us with x is equal to 2 raised to the y minus 2. And then finally plus a 3. So we can go ahead and use this to our advantage to figure out what values we're going to get here. So in this case, let's go ahead and replace it here. So we were going to go ahead and write x is equal to 2 y minus 2 and then finally plus a 3. So this is where picking our y's is very important. So we're going to go ahead and figure out our y values, and then from that we will get our x values. So if we plug in a 0 for y, that will give us, in this case, a 2 raised to the 0 minus 2 plus a 3, or an x value of approximately 3.25. If we plug in a -1, so that should get us approximately a 3.125. Now if we pick a value of y as 1, we should get a 3.5, and additionally points of 2 and 3 should give us a 4 and a 5. So we're ready to graph this. Let's go ahead and see what we have. So we have, in this case, a 3.5 and then a 1. So 1, 2, 3, and then 4. So 3.5, 1 is approximately right there. A 4 and then a 2. So 4, 2 is approximately up here. Additionally, we have a 5, 3. So 5, 3 is going to be all the way up here. And last we have our value of a 3.25 and then 0. So 3.25 and then 0. And then finally a 3.125 and a -1. So 3.125 and then -1 is approximately down here. So connecting our dots, we should get an approximate graph that looks like this. Okay, so what we have next are properties of logarithms. So properties of logarithms. For x is greater than 0, y is greater than 0, a is greater than 0, and a is not equal to 1, and we have our real number r, we're going to go ahead and have these different types of properties for our logarithms. So our first one is going to be our product property. So say, for example, we had our log base a and then xy. Well, we're going to go ahead and keep our same bases here. So same bases of a's. And we're going to go ahead and have our x So our x, log base a of x, and then log base a of y. So if you see that they're multiplied by each other, you can go ahead and pull them apart by having log base a x plus log base a y. Now, additionally, with our quotient property, it's very similar, but now we're dealing with division. So log base a, and then we have x divided by y. We can go ahead and pull these apart. And the major difference between these, instead of a plus, we have a minus here. So next we have our power property. So log base a of x raised to the r. What do? Well, basically we take that r and then we bring it down in front. So we take that r and then bring it down in front, and that is where it goes. So our last two here, we have logarithm of 1. So log base a of 1, if you see that, you're going to have a 0. Base a, logarithm of a. So say, for example, you have log base a of a, that is going to be equal to a 1. So let's go ahead and use these properties of logarithms with some of our examples here. So our first one, log, in this case, base 7, and then we have an 8 times a 6. So this is going to be an example of our product property. So if we go ahead and look back up, product property, again, because we have two numbers multiplied by each other. So let's go ahead and write this out. So we want to go ahead and use product property. For this one. So we can go ahead and rewrite log base 7, and then we can have an 8. And using our product property, we know that we'll have a plus in between. So log base, and again, keeping the same base of 7, and then we have a 6. So next one, we have division. So we can go ahead and use our quotient property. So using our quotient property, in this case, we will have log base of 6, 12, and then minus log base, in this case, 6. We want to keep our same bases, and then 5. So as you can see, we have the 12 here, and additionally, we have our 5 here, and then our 5 here. And then we kept our same base of a 6. So this next example, we're going to go ahead and try to rewrite this one. So let's go ahead and try to rewrite. How can we do this? Well, we can have, in this case, a log base 2 and rewrite that 9 and raise it to the 1/3. So in this case, we have 9 raised to a power. So let's go ahead and use our power property to bring that power down. So power property. So we're going to go ahead and take the 1/3 and then just bring it out in front here. So that should give us a 1/3 of log base 2 and then 9. And we should be good to go for that one. So additionally, we have part D here. So let's look at part D. Part D, we're going to go ahead and try to rewrite this one as well. So let's go ahead and try to rewrite. This is going to be log base of A, and then r raised to the, well, the top number is going to be what we raise r to, so in this case a 3, and then the number associated with our radical is going to be the bottom, or the 5. So again, we can go ahead and use our power property here and bring this fraction or exponent down to the front. So that will give us a 3/5, and then log base a, and then finally r. So our next example here is a little bit more complex. We're dealing with log base of b, and then we have a fraction of r, s raised to the 2, t, and then divided by u raised to the 3 and v to the 5th. So our first thing we want to go ahead and do is use our quotient property. So let's go ahead and use quotient property and split this division up here. So use quotient property. In this case, we know that we'll have a log base b, and then we'll have the top portion. So that is going to be r, s to the second, t, and then when dealing with our quotient property, again, we'll have a minus here, and then log base b, and then what is our bottom? Well, we have u raised to the 3rd, and then finally v to the fifth. Okay, so let's go ahead and see what we can pull out from this one. Well, we have a lot of stuff multiplying. We have 3 things multiplying in the first part, and then we have 2 things in the bottom. So let's go ahead and try to pull these apart using our product property here. So use product property. So using our product property, we can go ahead and pull this apart. Our product property stated that as long as we have our same bases, we're going to go ahead and add those together. So in this case, log base of a b, and then we have an r, plus log base, in this case a b, and then what do we have? We have an s to the 2, and then last we have a log base of b, and then our last piece that we had multiplying was this t. So we still have minus, and then what do we have now? Well, we are subtracting, in this case, log base b, and then we have u to the third, and then what else can we do? Well, we can go ahead and split this one up as well using our product property. So this will give us plus, in this case, a log base b, and then v to the fifth. Okay, so what do we need to do next? Well, it looks like we have several powers here. We have a power here, and we have a power here, and last we have a power there. And we want to go ahead and try to bring those down and figure out if we can further simplify. So in this case, we need to use our power property. So log base b, and then r, nothing to bring down, but this next one we can go ahead and take that 2, bring it down to the front using our power property. So that'll be 2 log base of b, and then an s, plus our second one, we don't have anything that we need to bring down. This next one, we do have something that we need to bring down, so let's go ahead and distribute this negative. So that will get us minus 3, go ahead and bring your 3 down, log base b, and then u, and then finally distribute that negative over to your second term here. So again, that'll be minus, bring your 5 down, so that will be 5, and then log base b of v. And that should actually complete it. It doesn't look like we can simplify any further here. So let's go ahead and look at our next one, which is f. So log base a, and then we have the mth root of r to the third, and then s squared divided by t to the fourth. So the first thing we want to go ahead and do is try to rewrite this dealing with that mth root. So rewrite. So if we rewrite this in our case, we should get a log base a, and then we will have r to the third, s squared divided by t to the fourth, and then that will be raised to the 1 divided by m. So what can we do now? Well, we can go ahead and try to bring this power down into the front using our power property. So use power property. So what will that leave us with? Well, it will be a 1m, and we will have a log a, and then we will have r to the third, s squared, and then divide that by t to the fourth. Okay, so now that we have established our next step, we can go ahead and try to figure out how to further reduce. All right, so let's go ahead and try to use our quotient property to further reduce here. So using our quotient property, we want to go ahead and write this 1 divided by m, and then we will have our log base of a, and then we will have r raised to the third, s squared, and then dealing with our quotient property, we have a minus log base of a, and then we will have t to the fourth. So next step, we need to go ahead and try to pull apart this first section because we have 2 things that are multiplied by each other. So that is a perfect candidate for our product property. So again, this will be 1m, and then we will have a log base of a. Our first term is going to be the r raised to the 3 plus log base of a, and then s raised to the 2. And then finally, minus log base a t to the 4th. So we want to go ahead and take care of these powers here and get them out to the front. So let's go ahead and use our power property once more. So this will get us a 1 divided by an m, and then finally a log base of a, and then r. So we brought this 3 out into the front here. And then finally plus 2 log base a of s, and then finally minus 4 log base a of t. So that should go ahead and complete that step. Let's go ahead and see if we need to do anything else to further reduce here. So in this case, what we can do next is go ahead and distribute that 1 divided by m by each of these different terms here. So what should that give us? Well, that should give us a 3 divided by m log base a and then r, and then finally plus 2 divided by m log base a of s, and then last we will have a 4 divided by an m and then log base a of at. Alright, so let's go ahead and look at writing each expression as a single logarithm with a coefficient of 1. So in other words, we're going from expanded all the way to a single logarithm. So for this first example, we have log base of 4x minus log base of 4y plus a log base 4 and then z. So we have the same bases here. Let's go ahead and try to rewrite this so that we can go ahead and use the product property first and then use our quotient property. So in other words, we will have a log base of 4, and then we'll have an x plus log base of 4 and then z, and then finally we'll have a minus log base 4 of y. Okay, so now what we can do is go ahead and use our product property. So in this case, we can combine them because we have a plus in between. So log base 4 and then xz, and then minus log base 4 of y. So now that we have a minus in between, we can go ahead and use our quotient property. So this minus tells us that we can use quotient. So log base of 4xz, and then our quotient property said that when we go ahead and try to convert back to our original here, we're going to go ahead and divide here. So we will have a log base of 4 and then xz divided by a y. Alright, let's go ahead and look at part B. So the first thing we want to go ahead and do is bring our exponents back up. So the 4 is going to go back up into the exponent as well as the 5 because of the power property. So that will leave us with log base b and then r raised to the 4th minus and then log base b of s raised to the 5th. So now what we can do is go ahead and use our quotient property, as we see that we have a minus sign here and we have both bases of b and our logs. So that should produce a log base b, and then our top is going to be r to the 4th, and then our bottom will be s to the 5. Alright, let's go ahead and try to look at part C here. So we noticed that we have some fractions out in front that we need to go ahead and put those back where they came from. So in this case, we can go ahead and take the x and raise it to the 1/3. And additionally, we can take this y and raise it to the 2/3. So that should give us a log base of a, x raised to the 1/3, plus, and then log base of a, y raised to the 2/3, and then finally minus a log base a, and then xy. So first of all, this plus tells us that we can go ahead and use our product property. So log base a, and then we will have an x raised to the 1/3, and then multiplied by y raised to the 2/3. Finally, minus log base a and then xy. So let's go ahead and look at this. So the subtraction symbol tells us that we can go ahead and use our quotient property. So that should get us a log base a. And our top portion is going to be this x raised to the 1/3, y raised to the 2/3, divided by, in this case, our bottom is going to be that x times a y. So The last step we want to go ahead and do is see if we can simplify any exponential fractions. So if we notice in this case, we can take our y 2/3 and we can go ahead and try to rewrite our top portion here. So in other words, a y to the 2/3 is really y to the 1/3 and then times 2. So in other words, we can take log base a and then we can take the third root of our top portion and then have an x and a y squared divided by our xy here. So looking at properties of logarithms with numerical values. So say for example we are given that log base of 7 is approximately 0.8451. Let's go ahead and try to find each logarithm without using a calculator. So the first thing we see is we have a log base of 10 and 49. Let's go ahead and try to rewrite this one. So rewrite. Well, 49, what that really is 7 times 7. And that will be perfect for our example because we have a 7 here. So let's see if we can rewrite this. Log base 10. And we said 7 times 7. Well, how else can we write a 7 times 7? How about a 7 squared? So using our power property, we can take that 2 and move it out in front. So what does that give us? A 2 log base of 10 and then a 7, which is exactly what we wanted because in this case we know that log base of 10, 7 is approximately 0.8451. So in other words, this is just 2 times log base 10 of 7. So we can go ahead and make a substitution. So 2 times 0.8451, and without using a calculator, we know that this should give us approximately a 1.6902. So looking at our second example here, we have log base 10 and 70. How else can we rewrite this one? So rewrite, and we want to go ahead and deal with a log base 10 of 7, or it might be useful if we had a log base 10 of 10 because we know that that is going to be equal to a 1 due to our base of log property. So well, let's go ahead and rewrite this as log base 10 of 7 times 10. That might get what we want. So 7 times 10, we can go ahead and use our product property here to pull it apart. So that would give us a log base 10 of 7 plus a log base 10 of 10. So log base 10 of 7, we know that's approximately 0.8451. So we can make a substitution here. Plus, and we know that log base 10 of 10 is equal to 1 because of our base of log property. So okay, so in this case, if we do the calculations, that should get us 1.8451, and we should be good to go. So our last topic here is going to be our theorem of inverses. So say for example, we have a greater than 0, a is not equal to 1. The following should hold true. So a raised to the log base of ax, that's just going to be equal to x. And log base a and then a raised to the x, that's just going to be x as well. So notice how our examples, we have 7 raised to the log base 7, 10. Well, all that's going to do is just be equal to 10. And then finally, we have a log base 5, 5, and then raised to the third. That's really just going to be equal to a 3. And then finally, we have the log base r raised to the k plus 1, and that's just equal to a k plus 1.